here. Okay, so our session's being recorded. So the problems that you're going to see in your new assignment for section 1.3 have to do with rates of learning and immigration and emigration and that sort of thing. And I think you're going to be fine with a little bit of thinking coming up with the differential equations for those problems. But the one area where I think you might need a little help is dealing with a series circuit. Now, this course is not formally a physics course. We have students in here who are majoring in other fields. But we do cover some basic physics, and this is why I'm covering this example with you. Okay, all right. Let me give you time to copy this example down. Okay, and then we'll talk about this example. Matthew, regarding your question, Matthew had a question about why the battery is the energy source, and the way this book does it is, so what Matthew's asking is, right here, this is the battery, and it's the energy source for the circuit. So it produces voltage. A battery produces voltage, so why not have a V there? The way the book does it is it has an E instead of a V. That's all. I think of it as energy, Hyung, but you've all had physics class. I mean, some of you had physics classes. You think of it the way you think's comfortable, but I'm good with energy. Okay, and so all right, I'll let you. All right, I'll give you a chance to finish copying. Okay, and just to comment here, so on this problem, the book calls the E, E is a function of t, time, and it's impressed voltage. That's what the book talks about, these LRC series circuits. In section 1.3, there's a little section on them, and the E, there with the circle on it is the battery source, and it's called impressed voltage, E of T. So that's what the book says, and so hopefully that's consistent with your other classes. Okay, so we have a series circuit here that contains a resistor R, okay, in the circuit, and a inductor L, okay, and then your battery source E. Okay, and what we want to do is we want to determine a differential equation. Determine a differential equation for the current. Current is denoted by I of T. Assuming resistance is R, inductance is L, and the impressed voltage is E of T. And they want you to use I for I of T in the answer and use E for E of T in the answer. So it's very important to follow these instructions that are given in the WebAssign problems, because certainly for your exam, you'll have problems that will have WebAssign instructions. And, you know, if you don't follow them and put in the right letters and so forth, it'll count the problem as wrong. And you don't want that, and I don't want that. So, you know, always look at the instructions carefully. Are there any questions so far? All right. Well, let me just sort of give you a little heads up here about a little explanation about this series circuit. So, the series circuit, they're different kinds. I mean, this one doesn't have, for instance, a capacitor in it, but it does have a resistor and an inductor. So the energy source, the battery E energy source, produces current. Current flows through the circuit. Okay. Now, like a resistor R is used in a circuit to help. You could be, for instance, trying to light a light, and maybe your energy source is putting out too much current. Well, the resistor can absorb some of that current so you don't burn the light out. Okay, so that's what a resistor does. And then you have an inductor L. An inductor L is basically it consists in the picture of coils, and coils. Let's assume current flows this way. Okay, let's assume current flows this way, Matthew. Matthew's asking which way does current flow. I didn't think about that, but I'm just assuming it goes that way, counterclockwise. So this L here is an inductor, and an inductor is coils that that using magnetism also store energy. Well, no, they store energy. Okay, so, and then if you had a capacitor on this circuit, you'd have a it'd be something like this on the circuit with a C on it, and a capacitor also stores energy. So, like for instance, why do you need energy stored? Well, like if you think about your cell phone, if you want to snap a picture with your cell phone, when you snap a picture, you're using a burst of energy. That energy has to come from somewhere. That would come from that could come from a capacitor. Okay, so capacitors store energy. Inductor, usually, from what I am reading, you have electric plates that store energy. That's a capacitor. We don't have a capacitor in this circuit here. But we do have an inductor. An inductor also stores energy using coils and magnetism, and it also modulates the current in the circuit so there isn't flickering. That's my understanding. And then you have resistance R, A resistor will absorb energy, so you have the right amount. So like if you're lighting a light switch, for instance, if the current's too much, the light switch will have a resistor on it, or the light will have a resistor on it, so that it controls the current and you don't burn the bulb out. Okay, so for how many of you does this is sort of a very fundamental explanation of a circuit, a series circuit. How many have seen this in another class? Maybe a simple physics class. And this, okay, Matthew, and does this correspond with what you've heard in other physics classes? Does this make, okay, Ann and David, okay, and Christopher for the most part. So we're good. Okay, we're good. And well, we have to have a differential equation. So what does a differential equation? What differential equation would be used here? What differential equation would be used for LRC series circuit? And if you don't know, I'm going to tell you, but maybe some of you have seen this. It's a law. It's a special law, begins with a K. That's right, Michael, Kirchhoff's law, okay, or Kirchhoff's law, okay. So I'm going to go to the next page here, and this is the law that is called, I've heard students pronounce it several ways, but how many have heard it used as Kirchhoff's law? Okay, how many have heard it as Kirchhoff's law? Okay, we'll go with Kirchhoff then. All right, so by Kirchhoff's second law, well, this is Kirchhoff's second law. Thank you, Andrea. Thank you, Andrea. Thank you, Kathia. This is Kirchhoff's second law. So what you're doing is the Kirchhoff's second law, it provides a balance between voltages. Okay, so your energy source produces voltage, but that voltage gets consumed in the circuit. It gets consumed in the circuit by inductors. So this term here corresponds to the voltage drop due to your inductor. Okay, and then there's a voltage drop due to your resistor, R. Okay, and then there's another voltage drop due to your capacitor, C. Now, in our problem, we don't have a capacitor, but we do have a resistor and an inductor. And incidentally, the voltage drop due to the resistor is the resistance R times the derivative of your charge, Q. That's what this term is. And the voltage drop due to the inductor is the inductance, which is given in Faraday's. Resistance is in ohms, right? So the inductance, L, times the second derivative of charge, Q. We use the book uses lowercase q for charge, Matthew. The book uses lowercase q to stand for charge. Okay, all right. So how many now is this, who have seen this, how many is this explanation ringing true with them? You have seen this in another class. I want to make. Okay, so Michael's seen it. The voltage drops, and okay, Michael, you have a thumb. Do I have a thumbs up from you on this so far? Okay, good. And Matthew, all right, Matthew, thumbs up. Good, good. Thank you, Michael. All right. So now what we're going to do is the derivative of charge is equal to the current I. So what we're going to do is we're going to replace here Okay, we're going to replace, well, if the derivative of charge is current I, then the second derivative of charge with respect to time would be the first derivative of current with respect to time. So you're replacing this second derivative here of charge with the first derivative of current. And then, of course, the derivative of charge with respect to time gets replaced with I. Okay, and it's understand I is a function of time, and you know, but we suppress the t. So now, since there's no voltage drop for the capacitor in this loop, we ignore that term, and this becomes the differential equation that will model the energy in our circuit. Now, if you have a different circuit, and in the homework you're going to see different circuits, you would have a different differential equation, but your starting point is always going to be Kirchhoff's law. Okay, that's your starting point. So now that we have this, we can solve the problem. We can solve the problem because what we need to do is we need to determine the differential equation for the current I, and so that means we have to express the I dt in terms of the rest of these variables. And so now it's just a simple matter of getting di dt by itself. Okay, a simple matter. And then, of course, remember it said in the instructions, use E for E of t. So I replaced E of t here with E, and this is the final answer. This is the final answer right here. Michael asks, will we be given series circuits in this course? Yes. Series circuits are an important application of differential equations. So you will be working with them. I mean, you will be playing with the differential equations. Let's put it that way for series circuits. Yes. But, you know, again, we are approaching this course assuming that some students maybe have not seen physics for a while, and so, you know, I take a very fundamental approach. Parallel circuits, you will see parallel circuits later on in the course, Michael. Yes, you will. And again, we'll take a very fundamental approach with those. All right. So this is the final answer. All right, let me see. Paige, for your exam, I would give you Kirchhoff's law. You would not have to memorize Kirchhoff's law. Okay, you're welcome. You're welcome.
Professor, you got a question?
Yes, yes. Yes,
thank you. So when let's say we convert everything to the terms of I, the first term for the inductor, we end up with L di over dt. What actually happened there? Can you go through that step
Well,
by.
if you have that current equals the derivative of charge,
Yes.
then what would the derivative of current be? The derivative of current would have to be the derivative of charge. And that's why the second derivative of charge equals the first derivative of current.
Oh, okay.
Just take this equation and differentiate both sides with. I'm not sure, Thomas. I'm getting a little echo there, but just take this equation and differentiate both sides with respect to t, and you'll see that the second derivative of charge with respect to time equals the first derivative of current with respect to time. Zachary, the fact, this is a definition that current, good question, Thomas. The current is the derivative of charge is a definition. Okay, that's where we got that. That's the definition of current. It's the flow of electrons through your circuit with respect to time. It's the rate of flow. So the first equation, let's see, Paige, hold on. The first equation is for charge. Yeah, well, the Kirchhoff's law can be expressed this way here, or it can be expressed this way. And sometimes one way is better than the other. For our problem, expressing Kirchhoff's law in this form was what we wanted, because we were trying to get a differential equation for di dt.
Okay, so they're both equivalent to each other.
Yeah. These two are equivalent. Absolutely.
All right, thank you.
All right, very good. Well then, so in section 1.3 now, again, you've seen some examples. Let me just see here. And just when you work on the new assignment, I think you're going to be okay. I think you're going to be fine with those problems. You're going to have to think a little bit to get the differential equation, but the new problems you're going to have for section 1.3 will not be as complicated as the assignment you had. But of course, the first assignment you had on section 1.3 had help aids, watching videos. So those were helpful. And again, I'm just trying to, I'm trying to show you a wide variety of examples in section 1.3 where you're modeling problems with differential equations. On that note, I will stop the recording for this lesson.